We're live. Okay, so chapter 15, we were talking about this question about they're adding toxins into the lake and watching fish die, basically. Kind of that's what is going on, though. All right, so notice in the computer output, it says log pollution. So which means if they take the log of the y, that means it's an exponential model, which we talked about yesterday. So when you, even though these are wrong, actually, they should have the log in front of the y hat like that. But you would say log pollution, and what's your slope? Or you could start with the y-intercept. That's usually we start with the y-intercept. What's the y-intercept here? Good. 7.5641 plus, and then we put what for my slope? 0.269. And then what's my x value? What is that? In context, what is x? Well, I think it's minutes, right? The time in minutes until fish showed distress was recorded. Yeah, I think this is minutes. You can put it right up there. Are you guys like following along with me? Okay, so which one is it? It's got to be 2, right? Okay. All right, now a 95% confidence interval for the slope. Again, it's b plus or minus t star times standard error of the slope. The standard error of the slope, just so to keep in mind, is, remember, when you take different samples are going to give you least squared regression lines, and the standard error of the slope is how off the slopes are from line to line. That's what the standard error of the slope means. So the b here would be what? Negative 1.03 plus or minus. Now the t star, again, 95% confidence. It would be inverse t. What's my area? 0.975, excellent. And how many degrees of freedom do I have here? Yeah, how do you know it's 16? It's n minus 2, and there's 18. Yeah, so it's 16, good. So we do inverse t, 0.975, comma 16, and we should come up with, anybody have it? Does anybody have it? Is it 1.96? Is it or is it not? All right, let me check then. Okay, so second bars, inverse t, 0.975, 16 piece, 2.12. Which one? This one, right? 5? Okay, now 2.12. Now, the standard error of the slope, again, this is the slope, and then look at standard error. So this would be your standard error of the slope. So that's 0.438. Thank you. All right. All right, so now the appropriate, why did I cross that out? Did I mean to cross that out? The appropriate null and alternative hypothesis to test the slope, the test statistic, and the p-value. Okay, so we kind of just started talking about this. The null for all of these is that the slope is equal to 0. So you're saying that x doesn't contribute to y, that x and y don't have a linear relationship. And then you're trying, the alternative would be that there is an actual linear relationship. So b is not equal to 0. So you want to show there is a linear relationship. Now, most often it's a two-sided test for these. And the computer output will also give you a two-sided p-value. So with that being said, or did it, wait, did this give us a direction on the slope? Hold on. Did it say it in there? Does it say that though? No, but does it indicate in the question that it should be like less than or no? You sure? It doesn't, right? Oh, I'm sorry. Oh, no, sure. Yeah, it doesn't say, right? It doesn't give us a direction on the alternative? No. Okay, yeah. So if it doesn't give you a direction again, it's just going to be the two-sided. All right. So now, so that means this is out. This is out. So now we're down to these three. All right. So now your test statistic is right. Where's my test statistic? That's your test statistic right here. Now you can test your test statistic. Test to see if it actually what it is. Okay, I'll show you. So your test statistic is t equals b minus b naught. In this case, b naught 0, so I don't even show it, over standard error of the slope. So what's my b? My b is negative 1.03, right, guys? SEB, standard error of the slope, that's right up here. So log pollution's right there, 0.438. That's your standard error of the slope. When I divide those two, what do I get? Negative 2.35. Oh, here it is. We were looking at the wrong thingy. Oh, no, we weren't. Were we? Yeah, I think we were. Guys. Yeah, I think you're right. Sorry, this was your test statistic right here. Negative 2.34. And then that's your p-value. My bad. Yeah. So with that being said, this is negative 2.34. It's got to be this one. Now the p-value is going to be right here. So this is test statistic. Sorry, messed that up before. And this is your p-value. Okay, let's keep going. The answer is 1. Okay. All right, suppose that inference for regression is conducted on the following small data set. I don't think that these even relate to the other one. I think they're just like, no, they relate, but they're not based off of that last problem. So you have 4 variables for x, 4 variables for y. What would the number of degrees of freedom be here? 2, right? It's n minus 2. N is 4. Because there's just 4 data points. Yeah, because remember, this is like 12 comma 2, and then 14 comma 3, and then 16 comma 5, and 18 comma 6. So there's 4 minus 2, which is 2. All right, 5. If the test of the hypothesis rejects the null in favor of the alternative, where b is the population regression slope. Okay, so they're rejecting this in favor of this. What is that saying? Is it saying the least squared regression line is useful for predicting y given x? Is that logical? It's not? Well, they're rejecting the null. The null is that they don't have a linear relationship. So like I know you gotta like kind of think a little differently for this one. The null for the inference for regression is that the 2 variables don't have a linear relationship. If you're saying you reject this in favor of this, it's saying that x is useful in predicting y. That they do have a linear relationship. And specifically, this is a one-sided alternative, said that as x increases, y increases because the slope is positive. Yeah, this one actually is 1. Like the slope. Oh, yeah, but I don't think this is based off of this. Yeah, I think they're isolated questions, 4 and 5. Yeah. But yeah, as this is saying as x increases, this is saying it's going up, right? As x increases, y increases on this problem. Okay. Yeah, 2 would be wrong because it's sloping upward, not downward. Um, what do we remember extrapolation? Extrapolation is bad. You should really only, if you're going to predict inside the data range, that's extrapolating. So this would be not good. Is not useful for predicting y given x. No, it is, because you reject the null. Has an intercept that is greater than 0. We don't really know that based on the information. Okay, oops. Let's keep going. Okay, is this the next question? Yeah. Okay. I don't know. All right, ready? Bryce, I'd ask you to read this, but I'm on the mic. Do you want to come up and read it? Yeah, no. Is it? Oh, Jonathan. We are on, what page are we on? We're on question 6 now. Oh, because I didn't know where mine was. I thought it was on the next page. Okay. A standard procedure to reduce abnormally rapid heartbeats in humans is called the diving reflex. These are interesting questions. This entails briefly submerging the patient's face in cold water. The reflex, triggered by cold water temperatures, is an involuntary neural response that shuts off circulation to the skin, muscles, and internal organs to divert extra oxygen-carrying blood to the heart, lungs, and brain. Interesting. A research physician conducted an experiment to investigate the effects of various cold water temperatures on the pulse rate of 7 6-year-old children. 6-year-olds. The temperature of the water is the explanatory variable, and the decrease in pulse rate beats per minute is the response. So, wait a minute. No, I was just thinking, so as temperature... Yeah, but they're saying it's in cold water, though, right? Yeah, so as temperature... So this is this way, right? Right? Because as temperature... As temperature... I did that right? Yeah. Because it would be... As temperature decreases... Well, this is increases. Am I doing that right? Yeah. Right. But how do I draw that? Oh, but they're just... Oh, because they're doing the decrease. Wait a minute. Yeah, as temperature decreases... Yeah, but if I go this way, like that... Right, so how should I draw this? It's fine? Really? Because I feel like that's not right. Yeah, I guess. Because this is temp. And this is... Wait, no. My bad. This is temp. I don't know, it just looks funky to me. Temp, and this is heart rate, right? So this is saying as temperature... No, see, that doesn't... All right, so just keep going. Okay. Do you want to fix my picture? Really? Right. Colder water makes your heart rate go down. So are they saying decrease in heart rate, and then it would be... But still, even if you did it this way... It says temperature goes down. It does? Okay. The higher temperatures have less decrease. Yeah, because it has to be negative. So it has to be this way. We should just do the problem, right? Wait. As temperature, yeah, so for higher temp, oh yeah, this makes sense now. Yeah. Okay. Yay. Okay. All right. So what is the equation of the least squared regression line in context? Bryce, what you doing? Yeah, why don't you help me with this one? So y hat equals a plus bx, right? And we have to define our variables. What's the y, guys, in context after we just kind of, a decrease, right? Y is the decrease. No, temperature is x. No, temperature is the explanatory variable. Temperature. So this is predicted decrease in pulse rate. And again, if you don't like to do it this way, you can define your variables off to the side. What's my A? What's my B? Whoops, it's a minus. And then it would be temp, right? Okay. That's the least squared regression line. I like doing this one at the end because it helps you guys remember everything, because I feel like you learn this and then we don't really see this again. So it's nice to have this at the end. Oops. Woo. Oh, absolutely not. No, we have a lot to do. All right. What is the slope of the least squared regression line? Interpret the slope in context of the problem. All right. What's the slope? Slope is... Don't do that. No, don't do that. Negative 0.8. No, don't. 1138. Thank you. I'm going to put this closer to me. Okay, so remember how to interpret slope. Change in y over change in x. So for every... What? Ooh. For every additional decrease in... Stop with that, Bryce. Put it away. For every additional decrease in... Or no, not decrease. For every additional... No, not decrease. No, for every additional temperature or degree. For every additional degree. Well, no, for every additional degree. Yes. For every additional degree. There is. That's why I make these folders for you. There is a lot of material. Oh, stop. I keep losing my train of thought here. For every additional degree, the pulse, or yeah, I was just going to say the pulse rate is predicted to decrease.
That's fine. That's right there.
You don't want me to write it like that?
Yeah, that's fine. Who cares? It's perfect.
Okay. The change in pulse rate is predicted to decrease by 0.81138. Okay. Don't. Okay. C says, you want to determine if water temperature is useful in predicting decrease in heartbeats. Formulate the null and the alternative hypothesis for the slope of the true regression line. Okay, so What would be the null?
Oh, B equals.
Yeah, big B is beta, is the parameter. That's the true slope. The true slope is 0, so that means it's not useful in predicting. The alternative is, yeah, not only if it's useful, but it's expected to decrease the pulse rate, right? Okay. Now, what is the value of the test statistic? So the test statistic, again, is T equals little b minus big B. And again, yeah, you totally can. I'm just going to show you how to do it just in case. Over SEB. Okay, so now this big B is always 0 here. Little b, what is little b? Negative 0.81138 minus 0, which I'm not going to put. Now, standard error of the slope, we got to look at our output. So again, we have, here's slope. So here's slope line, right? Like slope band, slope line. Standard error of the slope is this guy right here. Yeah, of the slope. It's standard deviation of the slope. That's what I was saying yesterday. I totally agree. Like I feel like it's. I wouldn't say that not a lot of questions. I would just say that when you do inference, that it doesn't actually. When you do inference, they don't usually give you the data and the conditions are met. I want this, let me go down again. Yeah. Why won't this let me go, guys? Crap. Oh, jeez. What am I doing? Not only am I recording right now, but I have to get through this. I don't know why I can't go down. So T equals negative 0.81138. And guys, what was that number? Standard error of the slope? 0.09038. And you divide those two numbers. I don't know why this wouldn't let me extend, but you divide those two numbers, and what should you get? Negative 8.98. Now, if you go back to the computer output, there's your test statistic right there. So did you have to actually show the work? No, it's right there. There's your test statistic. But in case it was a multiple choice question, they asked you to calculate it. I want you to know how to calculate it. Now, if you move over, what are you seeing? P-value. And what is the p-value basically? Majorly statistically significant. So how many degrees of freedom? No, there's how many? There's 7. Yeah, there's 5 degrees. How do we know how many in our 7? Magic word 7. So then it's n minus 2. So that's 7 minus 2, which is 5. Okay, so now the p-value for this test is practically 0. So I showed TCDF. Not that you have to do this, but again, if you don't have the data for this test in your calculator, you can't run a regression like we did for all the, you can't run an inference test like we did for all the other tests. So if you were to actually calculate, like try to find the p-value, the null is 0, so the slope is 0. That's your test statistic. So if you were going to do TCDF, and let's just do that for a minute. So like normally we do normal CDF, but if you do TCDF, the lower would be something really, really low. Then upper is your test statistic, which is really far out. That's almost 9 standard deviations, which is why your p-value is like non-existent, and there's 5 degrees of freedom, which is super, super low. So 0.0014. Okay? Okay, so it says, does water temperature appear to be useful for predicting the decrease in heart rate? Use the significance level of 0.05. So if alpha is 0.05, there's my p-value. Would I reject the null? Yeah. Findings are statistically significant, and we would say that water temperature does appear to be useful for predicting the decrease in heart rate. Okay, and now I'm just going to leave this up actually. Yeah. I just wrote alpha is 0.05 and reject the null. All right, now H says find the 90% confidence interval. So we rejected the null, right guys? Right? So now again with that duality concept, should 0 be in this interval if we reject the null? No. That's like a biggie. They ask that a lot. Yeah, sorry. So you have the confidence interval again is just b plus or minus t star times standard error of the slope. You have your you have your slope at negative 0.81138 plus or minus. How do we get the t star? Inverse t. If it's 90% confidence interval, what's the area to the left? I don't know. I'll get there in a minute. Inverse t, what's the area to the left, guys? 90%. 0.95. Because remember when you do 90% confidence interval, 0.90 is in the middle, and there's 5% in the tails, and this would be t star. So, and then the degrees of freedom was 5. So that should come out to be your t star. This is standard error of the slope, which they give you on the computer output. And then you get this as your confidence interval. We rejected the null, so 0 shouldn't be in that interval. And then again, remember, the interpretation for these confidence intervals are slightly different. We are 90% confident, and then you kind of do it as we interpret slope. So for every additional degree in Fahrenheit, the decrease pulse rate on average, I should say the decrease in pulse rate, right? Decrease in pulse rate on average. Well, wait. Oh, no, that's why. Well, the decrease in pulse rate on average decreases. Isn't that too many decreases? That's why you said the change, right? So the change in pulse rate on average decreases between. Okay, let's fix this. The change in pulse rate on average decreases by 0.99 to 0.62, I would say, beats per minute. Okay. All right, so that takes care of like the notes, but let's now start the frappies. So go to the frappies. Yeah, no, you want me to do the frappies because if we can bang out, how many frappies are there? 3? It's the frappies. How many are there? There's only 3, no? All right, so let's get through some of these. It should be just the next page. Are you sure? I thought there was 3 frappies. All right, let's bang out some of these frappies. At least we can do the next 2, right? At least. Ooh, this one's actually even done. Well, yeah, but let's actually go through it though. Okay. All right, stop talking. Shh. A manufacturer of dish detergent believes the height of soap suds in a dishpan depends on the amount of detergent used. Well, that makes sense, right? The more detergent you use, the higher the suds. A study of the suds height for a new dish detergent was conducted. 7 pans of water were prepared. All pans were of the same size and type and contained the same amount of water. The temperature of the water was the same for each pan. An amount of dish detergent was assigned at random to each pan, and that amount of detergent was added to the pan. Okay. Then the water in the dish pan was agitated for a set amount of time, and the height of the resulting suds was measured. So a plot of the data in the computer output from fitting a least squared regression line to the data are shown below. Okay, so this would make sense that as you increase the amount of detergent used, your sud height should get bigger. Yes, Alex. Go quick. Okay, so now I will erase this. Okay, so you have your amount, which is your explanatory variable, that's your x, and that's your slope, right? Now look, standard error coefficient. This would be your standard error of the slope, right here, the 0.7553. This would be your test statistic, and that would be your p-value. So you can see it all here. And now the S is the standard deviation of the residuals. That's right here. And you can get R from R squared. So that's everything. And then you have your y-intercept. So I'm going to undo what I just did because this I felt like looked nicer. Yeah. Okay. All right. So now A says, write the equation of the fitted regression line. Go ahead. You can copy that down. So predicted height, instead of writing the word predicted, you could just put a hat over it. Yeah, you could put height with a hat on it instead of writing predicted height, but that's what the hat means, predicted. There's your y-intercept plus 9.5000 amount of detergent in grams. Okay. So it says, note that S equals 1.99821 in the computer output. Interpret this value. So here, you can write this down too. Now remember, S is the standard deviation of your residuals. So it's basically your prediction error when you use your least squared regression line. So you always want your S to be small. So I put here, when using the least squared regression line, and again, feel free to always use LSRL, because that's the abbreviation for least squared regression line. Your prediction will be off by about 2 millimeters in height of soap suds. How did I get the 2? Well, this is really close to 2, 1.99, and I knew it was millimeters because that's the way they're measuring height. Okay, and now it says identify and interpret the standard error of the slope. So we've talked about this, but not in great detail. That's why I like this frappy. So here, standard error of the slope. So now, on average, the slopes of the least squared regression line from any sample taken from this population will deviate 0.7553 from the true least squared regression line. I kind of like, what did I put here? Yeah, I feel like I would have said something like what I have right here, even though this isn't wrong. It's a nice way to put it. I put the standard error of the slope estimates the variability in the sampling distribution of the slope. How much we expect sample slopes to vary from experiment to experiment. That's what I have down here too. So either one. Good on that, Freppy? Okay, let's start the other Frappy. Let's see if we can bang this one out. Then you guys only have two more to do, right?
Can you put the answers on the classroom?
Yeah, well, all these Frappies you can look up. Just start, like, Googling them, and they come up. As far as the multiple choice, though, I was going to scan in all my multiple choice packets and the answers so that you guys can check it and be like, all right, I get that, I don't get that, and then you can know what to ask me. I I just want to start review. Yeah. Like, so these are just like for you to get your head, like wrap your head around 13, 14, 15 and let's just try to review as much as we can when we get back. I'm going to try to finish this. I only have one question to grade and then I want to post the grades before I leave today. Okay, let's do the next one. Okay. All right, so the next one says, what does the next one say? Nope. I have this one over here. Okay, John believes that as he increases his walking speed, his pulse rate will increase. He wants to, what does that say? Model this relationship. John records his pulse rate in beats per minute while walking at each 7 different speeds in miles per hour. This is kind of stupid. Doesn't he know that? Sorry. If you're walking faster, isn't your heart rate going to go up? I'm not sure about that. All right, so what's important here is it's an easy frappy to wrap your head around. Now you just have to make sure you understand how to look at this computer output. They're all pretty much the same. So you got your speed, you got your slope right here. This is standard error of the slope. It's in the line of the slope. You got your test statistic, which is really big, and a really, really tiny p-value, which makes sense because your test statistic is 19. 19.88. That's huge. Okay, now this in the bottom here gives you your degrees of freedom. So why did they do it like that, though? How many is there? 1, 2, 3, 4, 5, 6, 7. Okay, so there's your 5 degrees of freedom. Why did they do it like that, but that's okay. All right, so again, predicted pulse, you're picking up the y-intercept, which is 63, plus 16.289, which is your speed. Just the speed. Okay, do your estimates of the slope and intercept parameters have meaningful interpretations in context of the question? If so, provide this context. This is like review. So the y-intercept, if this is his pulse rate and x is 0, what does that mean? Yeah, this would be John's resting heart rate, that's the y-intercept. Now to interpret the slope, for every additional mile per hour, John's heart rate on average will increase by 16.289 beats per minute. So that's review. What's new is part C. John wants to provide a 98% confidence interval for the slope parameter in his final report. Compute the margin of error that John should use. Assume that conditions for inference are satisfied. Yay! Okay, now the confidence interval, B plus or minus, figures out the point estimate and goes the margin of error on either side. The margin of error, though, is only the T star plus or minus SEB. So that's your margin of error. not the b plus or minus, because that creates the interval. This just creates the width, like how far am I going out on either side. So SEB, well, first you have to figure out the t star. So that's, if it's 98, there's 0.02 for each tail. You divide that by 2, so that'd be 0.99. Degrees of freedom is 5. There's 7 data points, so n minus 2. So then you do inverse t, 0.99, comma 5, and you should get 3.365. Your standard error of your slope is 0.8192, which is right up here under that blue line. And then that's your margin of error. And that's it. All you have to do is find the margin of error. That's nice. Okay, so this was good. So I don't know that I have to do a video for chapter 15. Yeah. Maybe. Yes, you guys too. Did everybody give me the yellow that's here? Have a fantastic break. Yes, enjoy yourselves. I will post this on my YouTube channel.